Welcome back to the tutorials for this week. What we'll do today is we'll go over some of the problems that is related to the organic chemistry classes that were taught this week. So, the first question that we will want to look at is in the following question, is that what is the major product formed from the acid catalyzed hydration of 3-methyl but-1-ene? Okay, so let us look at the name of the structure of this compound. It is 3-methyl but-1-ene, that is basically 3-methyl 1-butene. Okay. So, all of you should take some time and write down the structure of this 3-methyl 1-butene, and so then after that we will be able to understand what the reaction is. Okay, so once you have written it down, so now the question is, what are the products of acid catalyzed hydration? So, just to recap, hydration is basically a reaction where, let us say you have an olefin and you add H2O, you get a molecule such as this. So, hydration is nothing but addition of water to the molecule. So, in this particular case, it is a olefin, and to the olefin formally what we are doing is we are adding a molecule of water. Okay. So, now in order to answer this question, let us first draw out 3-methyl but-1-ene, so which I am assuming that all of you have already drawn. Now, let us look at an arrow pushing mechanism. So, what I would expect is that since this is an acid catalyzed reaction, so I would have H3O plus in the medium. So, just to draw out H3O plus, it is O, H, H, this is water, and water has 2 lone pairs, and so one of the lone pairs is now donated to H plus, and so you get H3O plus. Okay. So, this H3O plus is basically protonated water. So, when you add H3O plus to an olefin, the arrow pushing mechanism will be the following way. So, you take this double bond from here, attack on this hydrogen over here for example, and then this bond breaks and goes to oxygen. Okay. So, in this process the bond between oxygen and hydrogen breaks and a proton is formally donated to an olefin. So, if you see here, now before we go further, let us number the carbons in this molecule. So, which I will do in a different color. So, we have, this is carbon number 1, this is carbon number 2, this is carbon number 3, and this is carbon number 4. So, here you have on the 3 position you have a methyl group. So, therefore, it becomes 3-methyl 1-butene. Okay. So, now once you add H plus to this molecule, you have 2 possibilities. One is that the carbon 1 reacts with this hydrogen here, and the product of this reaction would be the H is over here, this is carbon 1, and then the rest of the molecule remains the same. Just to go through the numbering once again, this is 1, 2, 3 and 4, and of course, the other carbon is number 5, but this is sufficient for us at this point. So, we have the H newly formed bond between carbon and hydrogen over here, and therefore, there must be a positive charge on carbon number 2. So, this is one possibility, and the other possibility is if we draw the same molecule and there is now a new bond between carbon 2 and hydrogen, and then in that case, just to complete the numbering 1, 2, 3 and 4. So, then there would be a positive charge on carbon number 1. Okay. So, based on the number of reactions that we have looked at so far and various stabilities and so on, it becomes quite clear that the carbocation on the more substituted carbon is more stable, and therefore, one would sort of suggest that this would be the more stable carbocation. Okay. So, based on this, now let us take the mechanism forward. So, I can safely say that this carbocation is less stable and therefore, it may not be formed. Okay. Now, coming back to the reaction. So, you have a carbocation that is being formed here, and now there are multiple things that can happen. Okay. If this carbon 2 which has a positive charge reacts with water which is remaining over here, as you can see this product is going to be H2O, and then eventually you would get an alcohol on carbon number 2. Okay. So, that is one possibility. Therefore, what can happen is that you can have this as the product. Okay. However, you might be familiar with the hydrate shift that can happen, that results in a more stable carbocation formation. And so, if indeed that happens, so imagine that this carbon hydrogen bond can actually migrate. So, the migration happens in the following manner. If it migrates, then you would end up with a carbocation such as this. Okay, so, the new hydrogen is over here, and here to just to keep the numbering the same 1, 2, 3 and 4. So, this is the kind of carbocation that you will have, which will give you eventually alcohol on carbon 3. Okay. So, these are sort of couple of products that I could imagine that would happen. Now, if I have to judge which one would be the major product, one could assume that the first step, which is the hydration step, would actually be a reversible step, because the elimination of the carbocation can again give you back the olefin, or it could give you a different olefin, that is a double bond between carbon 2 and carbon 3, which can again pick up a proton and generate eventually this more stable carbocation. Okay. So, what I would suggest is that this carbocation that is formed here is the more stable carbocation, and therefore, this would be the major product. Okay. Now, let us look at the solution. So, here that is the possibilities are, this is product 1 where only Markov-Nikov addition has happened, product 2 in which you have Markov-Nikov addition product plus 1,2 hydrate shift, which is basically this molecule. Product 3 is Markov-Nikov addition and the 1,2 methyl shift, that is there is a methyl group that has moved from to form a different carbocation, and the last one is the anti-Markov-Nikov addition product. Now, in order to address this question, we have already looked at the mechanism, we have already looked at the major product. Now, let us eliminate the possibilities. Okay. So, this I would argue that is this would be a minor product at best if it is formed at all, right. So, therefore, this will not be the major product. Now, we just looked at the possibility of one being a product, but we also ruled out one being a product because it could be a reversible reaction and eventually it will form the more stable carbocation. So, the more stable carbocation is basically giving you this product. Now, between a hydrate shift and a methyl shift, one would argue that a hydrate shift is more facile. Second thing is that the hydrate shift actually gives you a tertiary carbocation, whereas in the case of product 3 you would end up with a secondary carbocation going to a secondary carbocation. So, just to sort of understand that better, let me explain it in the following way. So, product 3 would be formed if you had a carbocation over here. So, I am keeping the numbering the same 1, 2, 3 and 4. So, if this undergoes a methyl shift, so it gives you a carbocation such as this. Okay. So, let me keep the numbering the same 1, 2, 3 and 4. Okay. So, a secondary carbocation is going to produce another secondary carbocation, which really does not help with the increased stability. Okay. So, therefore, the product 3 would be less likely, right. So, the correct answer here would be 2. So, that is shown here, only Markov-Nikov addition product with 1,2 hydrate shift. Now, let us move on to the next question. So, here we are looking at a hydroboration oxidation reaction. So, consider the following reaction where you have this methyl cyclopentene undergoing hydroboration followed by oxidation with hydrogen peroxide. Now, let us look at the products that could be formed. So, here are 4 products that are listed out and there are choices given. Okay. So, now how do we address this question? So, when we address this question, let us go back and look at the mechanism of this reaction, right. So, the mechanism of this reaction is that there is first a borane addition followed by oxidation. Okay. So, if you look at how the borane addition followed by oxidation happens, you have an olefin with a methyl group here. Now, you are formally adding BH3 here. Okay. So, BH3 would add to the double bond and there are 2 possible products. So, one is BH2H and the other product is H followed by BH2. Okay. Now, let us do the products of oxidation. So, if this undergoes oxidation, then this boron will be replaced by oxygen and therefore, you would get OH, and if this undergoes oxidation, then this boron would be formally replaced by oxygen and you would get this product. Okay. So, imagine that this is R and this is R. Okay. So, when hydroboration oxidation happens, formally first a borane adds to the double bond and you get BH2, which is followed by an oxidation reaction which can give you the alcohol. Okay. So, now before we go forward, we need to first figure out which product is formed in major quantity. Okay. So, from based on what we have learned so far, the borane ends up on the less substituted carbon. Okay. So, therefore, when you have a choice of more substituted carbon versus a less substituted carbon, the boron ends up on the less substituted carbon and therefore, this compound would be the major product. Okay. So, in this particular example, what we are looking at is basically this molecule here, and we also know that the stereochemistry of addition is syn, that means that the boron and hydrogen end up from the same phase, and so therefore, we also have a stereochemical sort of restriction in this molecule. Okay. So, since we need to look at stereochemistry as well, let us first draw out what we would expect. Let us say it comes from the bottom phase, then you have CH3 and the OH would end up here and the H would end up here. In case the borane adds from the top phase, then the CH3 would be below and the OH would be above the plane. Okay. So, clearly if you look at the answers that are given here, from a stereochemical standpoint, the anti-addition is not possible and therefore, you can eliminate the choices of 3 and 4 based on this. And so, the only 2 choices of the correct answer are 1 and 2, which is basically answer B. Okay. The next question here is, which statement about the above hydroboration is incorrect? Okay. So, keep in mind what we are asking is which of the following statements is incorrect. Okay. So, the first choice is BH3 acts as an electrophile. So, based on our understanding of an electrophile is something that reacts with a pair of electrons or a negative charge. So, borane being electron deficient, it is a very good example of an electrophile. So, therefore, this statement is correct. The second statement, which is the reaction proceeds via syn addition of BH to the double bond, based on stereochemistry, we have already described to you that the BH acts from the same phase, that is the boron and hydrogen act from the same phase. We have plenty of experimental evidence to show that. Okay. So, therefore, B is also correct. C, addition of BH to the alkene is Markovnikov addition. So, here we know that eventually the OH ends up on the less substituted carbon. Therefore, this would be an anti-Markovnikov addition. Okay. So, according to Markovnikov's rule, the substituent should end up on the more substituted carbon. So, here therefore, C would be the incorrect statement and D is related to C, in which case the statement says that BH addition is an anti-Markovnikov addition. So, therefore, D is correct, and so the correct answer to this question, which is which statement about the above hydroboration is incorrect, the answer would be C. In the next question or the next part of this question, the question is the hydroboration reaction proceeds via A carbocation intermediate, B a triangular intermediate, C a cyclic 4-membered transition state, and D a carbanion intermediate. Okay. So, in order to address this question, let us look at the mechanism. So, in the mechanism that is proposed here is that the olefin reacts with the BH bond in the following manner, that is, you have the olefin reacting at the forming a bond with the boron, and the boron hydrogen bond also breaks and it forms a 4-membered cyclic transition state, wherein the boron ends up on the less substituted carbon. So, therefore, the formation of a carbocation intermediate is incorrect, a triangular intermediate is also incorrect, the carbanionic intermediate is also incorrect, and the correct answer is that it forms a cyclic 4-membered transition state. The next question is, what happens when ozone is added to a terminal alkene such as pent 1-ene or 1-pentene followed by treatment with dimethyl sulfide. So, there are 4 choices given here, that is 2 ketones are formed, an aldehyde and a ketone is formed, a diol is formed, or 2 aldehydes are formed. So, in order to address this question, let us first look through the mechanism of ozonolysis. So, here as we have discussed in class before, the olefin reacts with ozone, which is a triatomic molecule, and in the following arrow pushing mechanism, it forms what is known as a major ozone based intermediate. Okay. And this intermediate then degrades or fragments to produce 2 products. Okay. So, it forms ozonide, which then gives you in this case 2 ketones. Okay. So, keep in mind that this is a internal olefin. Internal olefin means that there are substituents on both sides of the olefin. So, you have R as a substituent here and it gives you 2 ketones. What happens when you have a terminal olefin? So, here is an example of a molecule with a terminal olefin, and so when this is reacted with ozone in the presence of methanol at minus 78 degrees, you get an intermediate such as this, which is then reacted with dimethyl sulfide to give you the terminal aldehyde, and of course, the other product there that is formed is formaldehyde. Okay. So, therefore, the correct answer is you would get 2 aldehydes when you react a terminal olefin. So, now to address the question, 1-pentene has the following structure. Okay. So, when 1-pentene is reacted, what you would get is this carbon-carbon double bond is broken and you would get an aldehyde plus formaldehyde here. Okay. So, the correct answer is 2 aldehydes are formed. Now, let us look through the next question. Next question is based on palladium catalyzed hydrogenation reaction. Okay. So, do not worry too much about the complexity of the structure. The question is fairly simple and straightforward. So, here is a cyclohexene molecule with some substituents around it, and it is exposed to hydrogen in the presence of palladium carbon, and then there are 4 choices given. Okay. So, we already know that hydrogenation reaction is a syn addition reaction. So, if you have an olefin such as this, right, you will end up with hydrogen being added from the same phase. So, let us say you have R1, R2, R3, R4. So, you will end up with R1, R2, R3 and R4. Okay. So, you have hydrogen being added from the same phase. It can be from the bottom phase or the top phase. So, here in this case, the molecule you are looking at has a olefin over here, and then there is a methyl, there is an ethyl, and then there is a isopropyl. Okay. So, here first what I do is I will just start numbering it. So, let me number it as 1, 2, 3 and 4, and now I would draw it in the chair conformation. So, the isopropyl group is most likely going to be in the equatorial position. So, this would be 1, 2 and there is an olefin between 3 and 4, okay. And then there is a methyl group and a ethyl group. Okay. It looks a little odd because it is little difficult to draw the olefin with the cyclohexane in it. What sometimes people do is that they draw the olefin like this and then it sort of makes it a little bit easier, but this is not very important for us at this point. So, therefore, I would still stick to this way of drawing it. Okay. So, now hydrogen can approach from the bottom face or from the top face. Okay. So, if it approaches from the top face, so what I will do is I will use orange to show the new hydrogen. And so, if we can now look at it, let me first draw out cyclohexane here, and if the hydrogen comes from the bottom face, I have exaggerated the hydrogens a little bit here, so that you get an idea about this is the ethyl group and this is the methyl group CH3 CH3. Okay. So, here the hydrogens approach from the bottom face. You could also have a situation where the hydrogens approach from the top face. So, I am just going to draw it similarly over here. Okay, so, here is the isopropyl group and now as discussed we will use orange. So, the top phase means the hydrogen comes from here and the other hydrogen is equatorial and the rest of the molecule is more or less the same. We have a methyl here and then we have the ethyl over here. Okay. So, these are two possibilities where the hydrogens come from the bottom or come from the top, right. Now, let us look at the answers as shown here. So, if you work out the possibilities, let us go back and look at the structures again. So, if you see in terms of stereochemistry, both hydrogens here are going to be in the same phase. That means that the methyl and the ethyl are cis to one another or syn to one another, and these two together are in this case they are all in the same phase. That means that they are all in the same phase from a stereochemical sense. In the case on the right, the methyl and the ethyl together, the relationship between two of them is cis, but together both substituents are trans to the isopropyl group. Okay. So, you have only two possibilities, that is the two hydrogens are going to come from either the bottom face or the top face, and that is going to give you two distinct stereochemical outcomes. Okay. So, if you go back and look at the solutions given here, so here this possibility can be ruled out because the methyl and the ethyl are actually anti to one another, which is not possible based on the mechanism that we have proposed. Similarly, this methyl and this ethyl here are again trans to one another, which is again not possible. So, therefore, the correct answer here is B, which is 1 and 3. Next question, what product would you expect from the following reaction? Okay. That is, you have a terminal alkyne which is reacting with HBr and it is going to give you 4 possible products. So, before we go ahead, let us look at the proposed mechanism for this reaction. So, if you have a terminal alkyne and if it reacts with, let us say HBr. So, here you have H plus reacting with the alkyne to give you a carbocation and Br minus. So, what would happen is you have what is known as a vinylic carbocation, right, And now if this reacts with Br minus, then you would get Br, CH3 and olefin. Okay. Since we have said that there is excess of HBr present, it is likely that this is going to react with another mole of HBr and you will end up with another carbocation. Either you will end up with this carbocation or you can end up with this carbocation. Okay. So, now to compare these two carbocations, one could argue that the primary carbocation might be more stable because it is not next to an electronegative group, but the other argument is that the secondary carbocation is more stable and it is next to a Br which is electronegative somewhat, but Br can also donate a lone pair of electrons and stabilize the carbocation. So, it is more likely that this carbocation shown here is formed and therefore, the next Br minus would attack here and the final product that is formed would be Br minus attacking here to give you the final product. So, let us look at the answer. The answer would be as shown here Br, Br, CH3, CH3. So, this would be 1, 2, 3 propane, 2, 2 dibromo propane. So, the correct answer would be A. Okay. Keep in mind you are dealing with excess of HBr. Now, the next question is what products would you expect from the following reaction. Okay. So, here again we have looked at this in detail previously. This is a hydroboration oxidation reaction, and so what we would expect is that the boron would end up in the less substituted carbon, and so therefore, the first addition would happen to the terminal carbon followed by oxidation, and now the oxidation would actually give you an enol. Let us look at the mechanism in the next page. So, to an alkyne you would end up with R C double bond C with BH H intermediate that is formed, which then is oxidized to give you R C double bond C OH. Okay. So, this is nothing but an enol and it is going to tautomerize to give you the aldehyde. Okay. So, therefore, what we would expect is addition of BH2 to an alkyne would give you an aldehyde. So, if you look at the solution as shown here, you would form first the addition of BH2 here giving you this borane over here, and then this borane is further going to undergo oxidation to give you the enol, which will tautomerize to give you the aldehyde. So, therefore, the correct answer here would be the product as shown in this, which is 2. In the last question, the question is using retrosynthetic approach, how will you get the final product from the starting reactant? Okay. So, we have already looked at retrosynthesis in the lectures. So, retrosynthesis is nothing but trying to construct a molecule through a systematic way from the product. So, therefore, if I have to look at this molecule, what I would do is I will first number the carbons, right. So, in my starting material I have 1, 2 carbons, here I have 1, 2, 3, 4, 5, 6. Okay. So, what I have done is I have added 4 more carbons to this molecule, right. But now not just that, we have one more very interesting situation here, in that if you look at carbon 3 and 4, the carbon 3 and 4 is actually a double bond, and on both sides of the double bond you have identical groups. That means you have an ethyl group on both sides. Okay. So, here is the olefin and you have ethyl or 2 carbon groups on both sides. Okay. So, now if I have to use retrosynthesis, what I would argue is that I would need to have addition of an ethyl group or to carbon number 4 and an ethyl group to carbon number 3 to get the final product. Okay. So, the retrosynthesis that I would propose would be based on addition of ethyl groups to the alkyne. Now, after we do that, we need to convert the alkyne to an olefin. So, we already know that an alkyne to an olefin can be done in couple of ways. One is through the syn addition hydrogenation reaction, and the other one is sodium and liquid ammonia. So, now let us look at the retrosynthetic analysis here. So, what we would propose is that the product, this can be obtained by addition of sodium and liquid ammonia. This in turn can be obtained from here by addition of ethyl bromide or ethyl iodide and sodium amide. Okay. So, this would be the forward synthesis that I would put forward to give you the final product.